In this lesson, we are going to learn two new valid inference rules, and-in rule and and-out rule. But before we do that, let's do a little review. We remember that validity has to do with the logical connection between the premises and the conclusion. We know that the form rather than the content of an argument shows the logical connection between premises and conclusion. We have learned that when proving validity, we disregard the content and pay attention only to form. If we can prove the form of the argument is valid, then we can prove the argument is valid. To prove an argument is valid, we should first identify the final conclusion and the basic premises. We should symbolize each statement in the argument. Symbolize the final conclusion, symbolize the basic premises. We should construct a proof table to demonstrate that you can get from the premises to the conclusion using a series of valid inferences. Symbolization. We have learned to symbolize so far two different forms of statements. We have learned to symbolize conditional statements. We have learned to symbolize conjunctions. Conditionals. If any statement that can be accurately paraphrased as an if-then statement is a conditional. The logical connector, if-then, is symbolized with the right-facing arrow. The part of the statement that goes with the if is called the antecedent. And when we symbolize, the antecedent precedes the arrow. The part of the statement that goes with the then is the consequent. When we symbolize a conditional, the consequent goes after the arrow. Now, it's really important that you learn these vocabulary words: conditional, antecedent, consequent. You will not be able to proceed with the rest of the logic lessons if you do not know what a conditional statement is, what an antecedent is, and what a consequent is. So learn those vocabulary words. One last thing about conditionals: neither the antecedent nor the consequent is asserted. The only thing that is asserted is the connection between the antecedent and the consequent. If the antecedent is true, then the consequent will also be true. The next form of statement that we have learned to symbolize is a conjunction. Conjunctions are statements containing two smaller statements joined together by the logical connecting words and or but, or any synonyms for and or but. We symbolize the logical words and or but with the ampersand symbol. Each of the smaller statements in a conjunction is called a conjunct. Again, an important vocabulary word you should know. The conjuncts are each of the smaller statements joined together by the logical connector and. Conjunctions are made up of conjuncts. Both conjuncts are asserted. We have also learned to symbolize statements with multiple logical connectors. More than one logical connector. To symbolize statements with multiple logical connectors, first, restate or paraphrase the statement using standard logic terms if, then, and instead of their synonyms. This will help you to identify each of the relevant parts of the statement. You need to identify each simple statement within the complex statement and assign each simple statement a capital letter. Remember, for this class, we have the convention of assigning the first letter of the bolded capitalized word to represent the simple statement. Important. When you're symbolizing a statement with multiple logical connectors, you need to figure out the logical form of the complex statement. What is the main form? The main form, the logical form of the statement, is determined by the main logical operator. You will symbolize the logic words or the logical connectives with the logic symbols that represent those words, an arrow for if then, and ampersand for and. When you have more than one logical connector, you must use grouping symbols to show the correct form of the statement. Remember that the main logical connector, the connector that tells us the form of the statement, goes outside of any grouping symbols. Finally, check your work. After you have symbolized the statement and put in the grouping symbols, translate your symbolization back to English to make sure that the way you've symbolized it accurately captures the meaning of the statement. Always remember, the main logical connector stands outside of any grouping symbols. The logical connector that's outside of any grouping symbols tells you what the main form of the statement is. Grouping symbols are so important. Grouping symbols are used to eliminate ambiguity, both about the main form of the statement and about the forms of the component parts of the statement. So much for symbolization. So remember, we're proving that an argument is valid. We identify the final conclusion and basic premises. We symbolize each statement in the argument. And then we construct the proof table to prove that we can get from the premises to the final conclusion using valid inferences. So, a quick review of proof tables. Remember, an argument is valid if and only if each inference from basic premises to final conclusion is valid. Proof tables demonstrate how to move step by step, line by line, from basic premises to final conclusion using only valid inferences. Each line of the proof table cites a valid inference rule, guaranteeing that each inference, each step in the proof is valid. An inference rule is a valid pattern of inference based on the form of the statements. An inference rule is a valid pattern of inference based on the form of the statements. And it's valid because the form of the premises and the conclusion are logically connected in such a way that if the premises are true, the conclusion is necessarily going to be true. The truth of the premises guarantee the truth of the conclusion of the inference. So far, you have learned one valid inference rule, arrow out rule. Arrow out rule says, from two premises, one of which is a conditional statement, and the other of which is a statement that exactly matches the antecedent of the conditional. From these two statements, you may infer the consequent of the conditional statement. Okay, that's the review. Now we're going to learn 2 new rules to use on our proof tables. And in rule. And in rule states, infer the conjunction of any 2 statements. It's that simple. From any 2 statements, you can infer the conjunction. You can infer the statement that connects the 2 statements with the word and. You literally put an and in between any 2 other statements. You literally put an and in between any other 2 statements. Here's an example. God is good. God is the creator of an objective moral standard. Therefore, God is both good and the creator of an objective moral standard. It is that easy. Don't overthink it. It really is that easy. You literally connect 2 statements with an and. Let's have another example. Basic premise G, basic premise C, infer G and C. You could also have inferred C and G. It doesn't matter. Both are correct. Which order you put them in is going to depend on how you're using them in the proof. In other words, you'll want to be strategic about which order you choose to put the 2 conjuncts in when you're applying and in rule. Let's have just one more, a little bit more complex example just to make sure you get it. Here's a statement. This statement is in the form of a conditional, basic premise H arrow K. Here's another statement, again in the form of a conditional, MNQ arrow B. We can apply and in to these 2 statements to create a very complex conjunction, H arrow K and M and Q arrow B. Okay, so you can apply and in rule to any 2 statements and infer the conjunction of those 2 statements. Let's move on to and out rule now. And out rule says, from a conjunction, infer either conjunct. Okay, so to apply and out rule, you have to have a conjunction. You have to have a statement whose main form is a conjunction. From a conjunction, you may infer either conjunct. Here's an example. Basic premise. God is both good and the creator of an objective moral standard. From this statement, which is a conjunction, we may infer that God is the creator of an objective moral standard. Right? We have inferred one of the conjuncts. How about another example? Basic premise, C and G. We may infer the conjunct C. Or we may infer the conjunct G. One more example. Basic premise. Notice that the main form of our basic premise is a conjunction. The ampersand symbol is the symbol that's standing outside of any grouping symbols. That tells us that we have a conjunction. If we have a conjunction, we can apply the and out rule. So, we can infer either conjunct. We can infer H arrow K. Or we could infer M and Q arrow B. From a conjunction, infer either conjunct. Okay, so we have learned and in rule, infer the conjunction of any 2 statements, and and out rule. From a conjunction, infer either conjunct. These rules are very simple, so try not to overthink them. They are as simple as they seem. They might seem overly simplistic, but remember that we are learning basic inference patterns, and basic inference patterns need to be self-evidently valid. What could be more self-evidently valid than if we have a conjunction, we can infer either conjunct, or if we have two statements, we can infer the conjunction of those two statements. In other words, it follows directly from the definition of a conjunction that either of the conjuncts is true, because conjunctions assert both conjuncts. Likewise, if we're asserting that two statements are true, it follows that their conjunction must be true, since conjunctions assert both statements. So while it would certainly be redundant if you had to spell these out when you were writing an argument, you don't have to do that. They're very useful when we come to proving that your arguments or other people's arguments are valid. That is, these inference patterns will help us prove that we can move from basic premises to final conclusion with valid inferences, even though in our own writing we wouldn't actually spell them out. So let me just show you how it works on a proof. Okay, first example proof. I've already symbolized these arguments for you. So we have our basic premise, D and E, D arrow F and E arrow G, therefore F and G. We notice, first of all, just that every statement in the argument is a conjunction. The main operator of each of the statements is a conjunction. First step, we're going to put our basic premises on our proof table, number our rows, we always look now to our conclusion, so our goal is F and G. So we want to strategize a little bit. I know that if I get F by itself and G by itself, I can apply the and in rule to get the conjunction of F and G. So I'm just going to set myself some sub-goals. I want to get F. I also want to get G. If I get both of those by themselves, I know I can use the and in rule to get this conclusion. Okay, so now I'm looking and I'm like, okay, I have three rules, and in, and out, and arrow out rule that I know how to apply. None of the two premises are conditionals. Both of the premises are conjunctions, which tells me, at least right now, I cannot use arrow out rule, because arrow out rule applies only if the main connector is an arrow, is a conditional. So what rule applies to conjunctions? Because these are both conjunctions. The only rule that applies to conjunctions is and out rule. So let me just apply and out rule. If I apply and out rule to line 1, I can infer D. I can also, if I want, infer E from 1 and out. Okay. Well, now I have some simple statements and some conjunctions. That doesn't really help me, but I can, again, apply and out rule to the conjunction on line 2, so I'm just going to go ahead and do that. Right, that is from applying and out to line 2, so 2 and out. And I might as well infer the other conjunction, the other conjunct of the conjunction on line 2. So E arrow G, I got that from applying and out rule to line 2. Okay. Obviously, I'm not finished yet because I don't have my conclusion, so let me go ahead and add a few more rows to my proof table. Okay. Row 7. Okay. 5 and 6 are conditional statements. So it's possible that now that I might be able to use arrow out rule because now I have some conditional statements. So to apply arrow out rule, I need a conditional statement and I need a statement that exactly matches the antecedent of the conditional statement. So look at the conditional statement on line 5, D arrow F. The antecedent of that conditional statement is D. Line 3 contains the formula D, which exactly matches the antecedent of the conditional on line 5, which means I can apply arrow out rule to lines 5 and 3. Arrow out rule says from a conditional statement, which I have on line 5, and a statement that exactly matches the antecedent of the conditional, which I have on line 3, I may infer the consequent of the conditional. F is the consequent of the conditional on line 5, so I may infer F using arrow out rule. But F was one of the sub-goals that I was trying to meet. And so I did it. So now I need to get G. Well, here's a conditional that has G as the consequent. If I have a statement that matches the antecedent of this conditional, I could infer G. The conditional on line 6 and the statement on line 4 match, right? The antecedent of the conditional on line 6 matches the statement on line 4, which allows me to infer the consequent of the conditional on line 6, which is G. So again, I applied the arrow out rule to the conditional on line 6 and the statement on line 4, and that allowed me to infer the consequent of the conditional G, which was one of my sub-goals here, G. Alright. Now I remember that I set those sub-goals because I was aiming for my conclusion. My conclusion was a conjunction. So I knew if I could get if I could get both conjuncts, then I could apply and in rule to get the conjunction. So now I have on line 7 F and on line 8 G. So I can apply the and in rule to line 7 and 8 to get the conjunction of those two statements on line 9. And now I have my conclusion. So you see how even though and in and out are not things you would write necessarily in an argument, they are certainly useful in helping us prove that this argument is valid. Let's do one more. Okay. Here's, again, I've already symbolized it for you. So let's put our basic premises on our proof table I and F. Basic premise. Second basic premise. Okay? Now I keep in mind my conclusion. I'm aiming for C. Okay? I'm aiming for C. I have on my proof table two basic premises. One is a conjunction and one is a conditional. The only thing I can do using the inference rules that I have right now is apply and out rule to this conjunction. So I'm just going to go ahead and do that. I'm going to infer this conjunct from the conjunction on line 1, 1, and out. I might as well just go ahead and infer the other conjunct. So 1 and out gives me F. Okay. Alright, so now what can I do? Well, here's a conditional on line 2. And I do at this point have the formula or the statement that exactly matches the antecedent of the conditional, right? On line 1 or on line 3 I have I, and on line 2 I have a conditional whose antecedent is I, so I can infer the consequent of the conditional on line 2, F arrow C. Right? F arrow C is the consequent of this conditional. So I used line 2 and line 3 I applied arrow out rule. Okay. Line 5 is useful because it's a conditional, so I might be able to apply arrow out rule to line 5 as long as I have a statement that exactly matches that conditional, which I do on line 4. So, conditional statement on line 5, statement that exactly matches that antecedent on line 4, I can infer the consequent using lines 5, lines 4, and arrow out rule. And now C was the conclusion I was looking for. Okay. So I hope that these two proofs have shown you how the and out and in rules are useful in proofs, especially when combined with the arrow out rule. In this lesson, you have learned the and in rule, infer the conjunction of any two statements. You have learned the and out rule. From a conjunction, infer either conjunct. And you have learned how to apply the and in and the and out rules on proof tables in combination with the arrow in rule.